So let's talk about the magnetic force on a current carrying conductor. Now, if a single particle feels a magnetic force when moving through a magnetic field, then a wire with a current moving through it must also feel a magnetic force. So here I have a wire, that's my orange line here, and I've got some box inside here where I'm going to place a magnetic field. Okay, so here I have my wire, and then I'm going to place a magnetic field in it into the board. So I'm going to make my X's into the board. Okay, now what's going to happen? Let's say that my current, let's see here, I've got my wire is going to be deflected to one side or the other depending on the direction of the current that's moving through it. So if I have my wire that has current that's running in this direction right here, okay, that means that my electron is going to be moving opposite the direction of the current. This is the direction of I down this way. My electron is going to be moving opposite the direction of current, so my thumb is going to be pointing back towards me. My fingers are into the board in the direction of the magnetic field, pointing down into the ground. And then not my palm, because that would be the direction of the magnetic force for a positive particle. For a negative charge for my electron, the direction of the magnetic force is going to be pointing out of the top of my hand here. And so the magnetic force is going to be pointing in this direction for this wire within this magnetic field, and that's going to deflect my wire toward this direction. Okay, and then we would see oppositely, if the current were running in this direction here, okay, if I was running in this direction, my fingers into the board, my thumb opposite the direction of the current, because that's the direction of the moving electron, and so then the top of my hand tells me the direction of the magnetic force, which is in this direction. Okay, so the moral of the story is that our wire can get deflected if there's a current moving through it and it's in a magnetic field. So what is this magnetic force on our current carrying wire? Well, we can write it like this. So we've got this force is going to be equal to the force on each charge carrier, which we already saw, QVB sine theta, where theta is our angle between the direction of current and our magnetic field in this case, okay? And then we multiply it by the total number of charge carriers. So we have to know the total number of those carriers per volume over some volume. So we've got the cross-sectional area of our wire A times the length of that wire L. Okay. So this is the magnetic force on our current carrying conductor. Now if you remember when we were talking about current, that the current is also equal to our number of charge carriers times the charge on those carriers, times their speed, times the cross-sectional area of whatever that current is moving through. So then we can derive, finally, this equation, maybe an easier way to use it for the magnetic force acting on our current carrying conductor, and that's equal to the magnetic field that conductor is experiencing times the current running through it times the length of that object times sine theta, where again angle theta is the angle between the magnetic field and the direction of our current.
The goal of this problem is to compare the magnetic force on a current carrying wire with the gravitational force on that wire, and we're going to consider the Earth's magnetic field. So my first, the beginning part of the problem, a wire is going to carry 22 amperes of current from west to east. So if I imagine my sort of coordinate system here, here's my wire, okay, and its current is going to run this way. We're going to call over here east and over here west. We're going to call up north and down south. We're going to assume that at the location where I'm standing on the globe, where I have this wire, the magnetic field is horizontal. That means it's flat on the surface of the planet where I'm standing. And it is directed from south to north. So the Earth's magnetic field at that point would be directed in this direction from south to north. And that it has a magnitude of the magnetic field of 0.5 times 10 to the minus 4 Teslas there. We're going to find the magnitude and direction of the magnetic force on this wire, which has a length, this wire is going to have a length of 36 meters. Okay, so we have this wire with 22 amperes of current running through it. I've got my wire oriented so that it's laying east to west on the surface of the planet. And at that point on the surface of the planet, my magnetic field from the Earth is directed from south to north. And we've got the length of our wire here of 36 meters. So with that information, we're going to find the magnetic force on this wire because there's a current running through it and it's located subject to the Earth's magnetic field, which has this magnitude at that location where I'm standing. Okay, so why, let's talk about why the magnetic field on the surface of the globe is oriented from south to north. So here I have my Earth, and you can imagine that the magnetic field of our Earth, there's like a giant bar magnet inside the Earth's magnetic field. The Earth's interior creates its own magnetism by a dynamo action, churning and spinning of the liquid metallic interior of the Earth generates this magnetic field through dynamo action. And currently, the magnetic field of our planet is oriented so that you can imagine a bar magnet, but the south pole end of the bar magnet is pointing toward the Earth's geographic North Pole. Okay, so the magnetic field lines around our Earth are going to be leaving from geographic south, arching over, and then entering into geographic north. These lines of magnetism, these are our magnetic field lines for the Earth, are directed away from a north magnetic pole toward a south magnetic pole. This is the orientation of that bar magnet that we can imagine located inside the Earth. Okay, so if I'm a person here on the surface of the globe, okay, I'm standing on the surface of the globe, I am experiencing at this point a magnetic field that is directed from geographic south to geographic north. And so that's why our magnetic field vector here is directed from geographic south to geographic north. Okay, we've got the current going to the east. So find the magnitude and direction of this magnetic force. Well, the magnitude of the magnetic force is easy. So the magnitude of our magnetic force will be the force on a current carrying wire in the presence of a magnetic field. So that force will equal our current times the length of our wire times the strength of the magnetic field times sine theta. And this angle theta is the angle between our direction of the current and the direction of the magnetic field. And in this drawing, my current and the direction of my magnetic field are perpendicular. So this angle theta here is 90 degrees. Sine of 90 degrees is 1. So this entire thing is 1. So the magnitude of the magnetic force is going to be our 22 amperes of current times the length of our 36 meter wire times the 0.5 times 10 to the minus 4 Tesla of the magnitude of the magnetic field at this location. So that gives us a magnitude of the magnetic force acting on this wire of 3.96 times 10 to the minus 2 Tesla. Okay, so, but we still have to figure out what is the direction. We've got the magnitude of the force, but what is the direction of that force? Now, I know that because of the magic of the light board here, when I do the right-hand rule, sometimes it's not exactly the same for you at home if you were to do the right-hand rule for yourself at home, because my image is being mirrored and flipped and so on. So in order to find the direction of this magnetic field, we're going to use our right-hand rule. For the right-hand rule, our fingertips point in the direction of the magnetic field. Okay, and our thumb points in the direction of the flow of the electrons. So if my current is going this way, that means that my electrons are going the opposite direction. They're going that way. Okay, so I'm on the surface of the globe. All right, so imagine that I took a piece of paper and I drew on my flat piece of paper here this exact image. Okay, north, south, east, west. Okay, and I turn it horizontally because that's the direction in which my wire is oriented within the magnetic field. Okay, so my fingers point in the direction of B, my thumb points in the direction of the flow of the electron. Okay, the electron's flowing opposite the direction of the conventional current. And since we're thinking about electrons in the current, it's the backside of my hand that's going to tell me the direction of this force. And so the backside of my hand is pointing up, and so that tells me that the magnetic force acting on this wire, because of the current in the presence of the magnetic field, the magnetic force acting on this wire is going to be directed upward. Okay, so that's upward. Whoop. Upward is the direction. All right, and now for part B. We want to calculate the gravitational force on this same length of wire if it is made of copper and it has a cross-sectional area of 2.5 times 10 to the minus 6 meters squared. Okay, and so we have copper, and we're eventually going to need this. The density of copper is equal to 8.92, it's just 8.92 times 10 to the 3 kilogram per meter cubed. And we're going to find the gravitational force, Fg. So the gravitational force here is going to be its mass times the acceleration due to gravity on our planet. Okay. Now, this G is 9.8 meters per second squared from last semester. The mass, what is the mass of our wire? We only know the density, we know the area, we know its length. Well, density is equal to the mass over volume. So if I solve this for mass, the mass is equal to the density of copper times the volume of this wire. Now we have, think about the wire as being a cylinder. It has some length and it has a cross-sectional area. The volume of a cylinder is its length times the cross-sectional area here, which is the area of our circle. So we've got the area here. That's the area. And we have the density and we know the length. So our mass is going to be the density of copper times the length of our wire times the cross-sectional area of the wire. Then our gravitational force will be density times length times area times G. Okay, so we've got 8.92 kilogram per meter cubed, and we have to multiply it by our length of 36 meters times, running out of room here, our area of 2.5 times 10 to the minus 6 meters squared, and then times 9.8 meters per second squared. Okay, and so that gives us a gravitational force of 7.87 newtons. Okay, now, I went ahead and took the mass and I plugged it into this equation, density times length times area. But if you're following along and you want to check, did you get the right mass? The mass by density times length times area will be 0.803 kilograms. Okay, so that's the mass of our length of wire. So we've got the gravitational force, 7.87 newtons. We've got the magnetic force, 3.96 times 10 to the minus 2 Tesla. Our gravitational force acting on this wire is much greater than the magnetic force acting on this wire. We can take the ratio of both of these to see how much larger the gravitational force is compared to the magnetic force. And if we do that, we take Fg and we divide it by Fb, the gravitational force over the magnetic force. We find that the gravitational force acting on this wire is almost 200 times larger than the magnetic force acting on this wire.